Все включено.
Ой, без скрепления? Специально есть? Все. Well, as I promised on the last lecture, today we will start from weak trick. I would like to recall the general formulation of the theorem I have conveyed in the very end of the previous lecture. Generally, we have 2 lectures left today and next week, and I hope very much that I will have succeed to at least say you the proof of H-topology theorem, at least with some missing technical steps. So sometimes I will miss several steps as exercises, otherwise I definitely will not be on time. So, drink. General situation is as follows: that we have 2 submanifolds R and S in a manifold such that the dimension is the sum of those dimensions. We have some dimensional restrictions. Dimensional restrictions are very important. And also these 2 submanifolds are transversal. And one of them is, I do not require that P is oriented, so we do not have generally an orientation of the whole manifold. But I would like that one of those manifolds R is oriented and another is co-oriented, which means that its normal quantity is oriented. So R is oriented, S is co-oriented, and then in this situation, since the sum of their numbers, of their dimensions is the dimension of the whole manifold, then transversality means that their intersection is a discrete set of points. So intersecting isolated points, and since they are, one is oriented and another is oriented, each point becomes assigned with a sign, depending on whether the orientations agree or not. And assume that P and Q are intersection points of opposite sides. So P, Q are intersection points of opposite sides. And also, we assume the following: that there exists 2 paths between P and Q. One path is, well, let this be R and let this be S. And one path in R and another in S. And both these paths together they form a loop. And I require that both of these paths do not go through other intersection points. So no other intersection points here. So this loop is a bed. And let it be a union of these two. paths. And a requirement is that there exists such A with these properties that it is constructible in V. So it is homotopically trivial in V. This is a requirement. And also a technical requirement is that, that such map is injected. Let us be more precise here. In the case, there is special case when R is 1. Yes, of course, in this, it is interesting only if both of them are. This is greater than or equal to 3, but at least 1. It is not interested when 1 is 0 at all. But there is special case R equal to 1 when this can be non-disconnected. And then this should be understood in the following way, that it is injected for any choice of base models. So it is injected for each connected component. And that's all. These are all conditions. And what is the assertion? The assertion is that there is an isotopy, an ambient isotopy of the whole manifold P. So it's P from P to the zero. Oh, sorry. With the following properties. That first of all, it starts with the identity map. We start from the identity map and we make some isotopy. We make some isotopy. This isotopy is trivial constant. Near all intersection points except for those two. So it is constant near R cap S without being. And the claim is that we can cancel those 2 points. So after an isotopy, R behaves like that. So after an isotopy, H1 R cap S is exactly all the same points without P and Q. So P and Q become cancelled. So that's general theory. Before starting proving this theory, let us discuss. Well, there are plenty of technical conditions here. Well, let us discuss that usually, in most cases, this list can be reduced very much. Namely, well, first of all, look, there is some strange asymmetry. We require this, but we do not require this for R. Why? The matter is that for R, it is always fulfilled. So, it is, I would like to leave it as an exercise. That if we have generally a manifold M and a submanifold M, and codimension is at least 3, then any loop in the component that is homotopically trivial in M is homotopically trivial in M without M. Any loop that is homotopically trivial in M is also homotopically trivial in M without M. Well, this is more or less intuitively obvious. If we remove from a manifold some codimension 3 or higher codimension subset, then this doesn't change our fundamental group. All homotopically trivial, all homotopy of the loop is something two-dimensional. This homotopy can be made disjoint from any codimension 3. I don't want to prove it explicitly, but more or less this is the proof what I said. Look, R has the dimension at least 3. So we can always make this homotopy non-intersecting to R. But for S, it is not always true. S can have the dimension less than 3. So we need to require this. So first, I would like to make several remarks. First, if R is also greater than the equal to 3, then this condition holds. If R is greater than equal to 3, then this condition is always true. Second, existence of such paths from B to Q here and here. There are no problems to go from B to Q in R, provided that R is connected. Well, and there is no problem to go from B to Q in S, provided that S is connected. Well, but here there is some problem. There is a problem when R is equal to 1. The matter is that, of course, it is always possible to come from B to Q in R, but if dimension is 1, then it can be not possible to go from B to Q without coming to other intersection points. It may happen that any path from B to Q in one-dimensional manifold goes through other intersection points. But if dimension is at least 2, then we can always avoid other intersection points. So, second remark is that if R is at least 2, S is always at least 2, and R and S are connected, then we always can find such a group A. But we also want to be contractible B. But we definitely can make it contractible B. If V is simply connected, then just it is always okay. So if this is and V is M, V is simply connected, then L always exists, and we do not need this always condition. Well, then L always exists. Generally, we could look on this theorem in the following way: that if we have two submanifolds and both dimensions are at least 3, and our submanifolds are connected, then just if we have any pair of points of opposite sides, we can cancel them. But if our conditions that both dimensions are at least 3 are not fulfilled, then we need some amount of technical conditions, and then we'll still uh, so well, that's a theorem. And the most important here, and the thing which can be avoided is this R plus S is this 5. And this is a crucial point which make an essential difference between all the differential topology starting from dimension 5 and dimension. So there are 3 walls: 3-dimensional wall, 4-dimensional wall, and 5 and 5. They behave completely differently. So now all these things about H-coborded theorem and so on, this is about 5 and 5. And this is exactly why we need 5 and 5, since it is necessary for integration. Well, now let us prove this. Proof is as usual. Proof goes the same way as more or less all proofs in this theory. Well, when we want to study a Morse function, we choose a nice coordinate system in a neighborhood of a fixed critical point. If you would like to study, well, a unique geodesic from last lecture, there was a unique, we have a unique trajectory from one point to another. We choose a nice coordinate system near this geodesic, near this trajectory, and now we would like to choose a nice coordinate system in some neighborhood of this of this edge. So now I would like to formulate lemma on how this neighborhood of A looks like. But I want not only neighborhood of A is a bad object, it is not simply connected. I would like to find a disk which whose boundary is this A, and we would like to understand that in some neighborhood of this disk we have some standard situation. And now I want first to describe standard situation. So how does this look? So gamma is as follows. Consider the following. In Milner's book is called standard model. It is not the total standard model used in physics, just the standard model for this particular situation. Consider just in two-dimensional plane. Consider two arcs. The smooth the smooth arcs which intersect transversally. Actually, it is very convenient to have that in neighborhoods of this point they are just straight and intersect orthogonally. So two very standard arcs. I could write them very explicitly, say some sign or something like that. But they're very standard arcs like that. And this will be called C, and this will be called C prime. And their intersection points will be A and B. And let us consider a small neighborhood. Some standard disk, D2 will be now D2 will be open disk, which is just the neighborhood of this here everything is very standard, just I don't want to write down. I could write down it completed. Well, we would like to multiply it by r minus 1, and multiply it by r s minus 1. Then all this object is r plus s dimension. And the idea is that I would like to model. Look, I would like that. I would like to show it in the following way. I would like that this C times this R locally movable R critical. And this C prime times this locally movable S. So the claim is that there is an embedding of this, thing into this is embedded of a submanifold of the same dimension. Well, if we have such an embedding, then I would like to denote its image by U. And which properties I want? I want that this embedding takes A to P, B to Q. It takes this red thing, C times R times this, is exactly the intersection of R with U. I mean this one, and phi of C prime times cross 0 cross this intersection of S with U. And also these C and C prime are come exactly to those two. Five C. Let us denote these two paths by this L consists of two paths. L1 is path between P and Q, and L2 is path between P and Q. I would like to have this. Actually, I'm not precise here. But to be precise, I should slightly extend L2 and L1. Slightly extend them, otherwise I cannot get it. So I always mean that I start slightly extend from that point. So this is exactly what we want. We want to say that the general situation is always modeled like that. But it is important that this is not completely local situation. We claim that there is extension of this to the whole disk. It is not only neighborhood of A, but we have this whole disk. This is the crucial point. Well, first let us. So lemma is that such an embedding always exists, and let us understand that this lemma implies theorem immediately.
Do we require that no other intersection points are in
This is exactly immediately from these two requirements. Because we do require this, but this follows from what I have agreed. So let us understand that theorem follows immediately from lemma. y lemma implies here. Well, look, this is a very standard picture, and of course we can do here a very standard isotopy. I would like to start moving this red arc and then move it here and here and here, and finally I move it. So it is not hard to make an ambient isotopy of this disk with the following property: that first of all I would like that this ambient isotopy is it starts from so plane. There exists an isotopy of this to this to itself. Ambient isotopy of this. I recall that this is open disk, but I would like that first it starts from identity. Second, it is trivial near the boundary. Is constant near. I'm sorry. Of course, open disk doesn't have a boundary, but I think you understand that it's trivial in some small string here. So of course, this isotope can be made trivial, and we can, without changing our near the boundary, we can push one arc from another. So our requirement is that G1 of C is disjoint from C prime. And there is no problem with doing this. And once we have found such isotopy, it is not hard to write down the whole isotopy, the required isotopy H. Our required isotopy H would be trivial everywhere except for this coordinate. Would be constant everywhere except for this coordinate neighborhood. This is a coordinate neighborhood. So I want to write it down only in this coordinate neighborhood. Of course, I would like it to be constant of some compact subset of this coordinate neighborhood. And well, how to do this? Let us choose any cap function, any function like that. This is a function which is a function on this space, which is 1 in a neighborhood of 0, and which is 0 outside some, as usual, we consider C infinity function, which is 0 of some compact subset, which is 1 near the origin, and which is C infinity here. And then using this function and G, we can just write down H explicitly. So I would like H will be will live on this. It will be isotopy of this coordinate neighborhood. So I would like to at any point in this coordinate neighborhood is a triple x, y, z. X is do this, y is here, and z is here. So it is written like that. I put here G with rho y z of x y z. That's all. Look, first of all, this is an isolate. Well, second, it is trivial of some compact subset. if we are of some open subset, then either y and z are large. If y and z are large, then this is just x, y, z. Then we have 0 here. This is x, y, z. Or x is near the boundary, and if x is near the boundary, then this is x independent of rho. So this is isotopy, which is trivial of some complex subset of this coordinate neighborhood, and hence it can be extended to the isotopy of the whole manifold B. So this is a well-defined isotopy of manifold B. And now look what happens with R and S. The matter is that the only intersections of R and S, they have x equal to 0. Oh, so sorry, they have y and z equal to 0. In both intersection points, which are inside our coordinate, y and z are 0. And this means that near this intersection point, we complete this isotopy up to the very end, and so we get rid of this of those intersections. Okay. So this is easy. If we prove a lemma, what is not easy, this is this lemma. But once we prove the lemma, theorem will be easy. So now I want to erase this and we start with discussing lemma. Well, lemma is proved by, we just step by step, we construct this file. We extend it from, but we need some, we need to be careful about several things, and at some point, this restriction plays a crucial role. Let us start. First of all, what we know? We know definitely that near points, we have already discussed this, near points P and Q in small neighborhood of them. Our R and S are organized in a very standard way. So near any transverse intersection points, which are manifolds, looks like in a standard way. And actually, we can start with, we can endow our manifold V with a remaining metric. And we can organize it so that near points P and Q, this remaining metric is such that, first of all, it is Euclidean near this point. Locally, it is just Euclidean metric. And these R and S are true orthogonal linear subspaces near P and Q. There is no problem with this. R and S, and here we also have R. Well, what's that? There is some idea what we want to do, and there are a lot of technical issues of how to do this precisely. And these technical issues can be made in several ways. Let us start with idea, and then I explain how to fill all gaps. What do we want? First, we want to extend to define our phi, only on this. Let us forget about that part and define it only on this. But indeed, first, let us forget on the disk also and define it only on those two curves. So first, I want to say that we can define. Sorry. That first, I would like to. First, let us look on a point A. I would like that. First, I want to define phi in the neighborhood of A. In the neighborhood of A, I just choose one straight. Yes. One more thing. When I organize very nice Euclidean measure in the neighborhood of A, I can require more. It is not hard to require that this arc L1 is also straight here. Also this is one-dimensional straight. Let us write down it like that. That R can be larger, but inside this R we have one-dimensional straight direction, and in this direction we have outgoing first A. And similarly here, we have R, and we have outgoing A. And there is no problem to map neighborhood of A. Yes, and similar, we have here a similar straight lines for factorial group. And there is no problem to map a standard neighborhood here to a standard neighborhood here, just in a standard way. Well, and map a standard neighborhood here to a standard neighborhood there, again in a standard way. Well, then there is no problem with extending these two whole arcs. Well, if we have a smooth arc here and a smooth arc here, then there is no problem to extend this map to the arc to arc, just any representation. Well, so we may assume that phi is defined on C cap C prime. C cap C prime cross 0 cross 0. This is more or less easy. Next, what we want next? Next, we would like to extend it to the disk. So we still do not want to think about those two factors, but we want to extend it to the disk. But before extending to the disk, first I would like to extend it to. Let's take one more. I would like to extend it slightly to a neighborhood of those two. I would like to extend it to a neighborhood of those two. Here, again, there is no problem with this. The matter is that, okay, I would like to, but the only thing is that when I extend my map to this green neighborhood, I would like that it is still standard near endpoints. So near endpoints, we always get into two-dimensional planes spanned by those. So locally here and here, we have the following. We have our whole manifold is R plus S, and which is decomposed as R cross S, and each of them is decomposed as so this is R, this is S, this is A1, this is A2, well, and these are some orthogonal. And what I want that when I extend to this small neighborhood, then I get into the product of those two guys. And there is no problem with this. But and a nice problem, a good question is why? Well, there is no problems with extension here and extending here. But the first question is why we can extend it along this path. And let us think about it. This is the first point where some non-triviality can happen. What do we have? We have here, we can find here such vector field orthogonal to this group here. And once we have already extended here, we have this vector field. It starts here and it finishes here. Well, and I would like to extend it to a non-zero vector field. If I extend a vector field to a vector field, then I can easily extend a map by using exponential map. So my goal is to extend this vector field near ends to a non-zero vector field on the whole arc. What can we say? When there can be a problem? Actually, there can be a problem only if this arc has two dimension one. But our we for sure are in situations when there are no problem. If we are in two-dimension at least two, then there is no problem with extending a non-zero vector field near ends of the arc when zero vector field is a whole arc. In codimension 1, well, if codimension was 1, then we could have this situation. It is impossible to extend it to 0 vector. Well, I always wanted to be orthogonal today. But we are not in dimension 1, so there is no problem at this point at all. In logical dimension, we always have rotated. Well, okay. So what happens at the moment? This was first step that we have defined on here. Second, we already know that phi is defined on a neighborhood of C in this disk. Only in this, we still do not think about these two guys. Next, I want to extend phi. So the third step is I would like to extend phi to the whole disk. Yeah, I always can assume that I need to extend on the inside. Here I just can choose my disk to be this name. So I only need to extend it inside the disk. And here, what do we see? First, we see that we can look on the, we have this boundary of disk to which I would like to extend my right. And this boundary, let me its image here, let it be L tilde. And this L tilde is, of course, what can we say? This L tilde is contractible in V because it is just homotopy today. Yes? And then, but so L tilde is contractible in V. But also, unlike L tilde lies here. In the so L tilde lies in the complement, actually in the complement to both S and R. Well, and using this property, we may say that L tilde is contractible in the complement. But also R has co-dimension at least 3, so it is contractible even in the complement of the union. Hence, L tilde is contractible in V without. So once more, we know that it is contractible in V. Then we use this property, this requirement that it is contractible in the complement to S, and then we can throw also R since it has logical dimension. So V is contractible here, and hence there is no problem to extend phi to a map. Our goal is to have this phi, we would like to be an embedded. But if we want to extend phi to a map of this, then there is no problem with this. Since this loop is homotopy 3. So there is no problem to extend phi to a map. So what can we get? What can we get at the moment? We get let us erase this. At the moment we get that let it be. So this is not our required file. It's some auxiliary map file. I just want to change notation. It is mapped from G2 to V with the following property that psi coincides with this phi near the union. But it doesn't coincide with it is by no means an impediment inside. But near this C and C prime, it is an embedded. So it is nice near C and C prime. It takes C and C prime to A and Z prime. It is embedded near them, but disk behaves hydrogen. What can we do? And here is the crucial point where this condition is important. And this point is completely the same as in weakness theorem in another theorem, by weakness in theorem on imbalance of manifolds in Euclidean spaces. You know that any, say, covert manifold can be embedded, but actually it is not important. It can be embedded in first of all, it can be embedded to large dimension R, yes, but actually it can be embedded to n plus 1, actually into n also, but it is not what I need now. If we have already an embedded to large dimension Rn, then we can just project it to smaller direction, Rn minus 1, along some direction. Completely the same technique works here. But we should be slightly careful. Look, what can we do? Of course, we can approximate this psi, we can obtain, we can assume that it is a smooth map, but not a smooth embedded, just smooth map. What can we do? Of course, we can always consider such tilde. I would like here to add some R content, so that we have map which is psi and something. It is psi on the first coordinates, and also I would like to add something to Rn. And then I can guarantee that it is an embedded. Well, moreover, let's here be high. Moreover, I can achieve that chi is 0 near boundary of a disk. Near boundary, I already have an embedded, so I do not need to correct to change anything. And it is, well, it is a good, so I can achieve that this is an embedded, and this is a good exercise to do this explicitly. To do this precisely, to prove this in detail, that we can always find this psi to sufficiently large Rn with this property, so that to make this psi tilde an embedded. And now I would like to start projecting to give so I would like to decrease this n by projecting. How to do this? Well, what I want to erase. So look, if we have this situation that I would like to decrease this n by 1, so I have here v cross Rn minus 1. No. So sorry. I have here this v, and I have here Rn. Well, and I've got an embedded of two disks. This embedded, and what I want, I know that near the boundary it is embedded in V. But further it goes like that. So this is this. I would like to project it along some one-dimensional direction. What do we know? I would like to project it so that it remains an embedded. So what is prohibited? It is prohibited to project along a line which intersects the two twice. So we get a map from D2 cross D2 without diagonal. To every 2 points x, y, we assign a direction of the corresponding line. And this direction, well, this one is L plus S dimension, and this one is L dimension. So this direction lives in RP n plus R plus S minus 1. And similarly, we also do not want to project along a line which is tangent to our disk, what does this mean? This means that I have a tangent bundle to the disk, and again to tangent bundle. Actually, I would like to have even on the unit vector tangent to disk, a unit tangent bundle to disk, and it also goes here to any point in any direction. I consider the corresponding direction in the total space. But now, look, this one is 4-dimensional. This one is 3-dimensional. This one has dimension n is at least 1 if we still want proceeding projection. Then
мы говорили какую-то тривиализацию, то есть как мы выглядим?
Yes, that's not. Oh, sorry. Yes. Yes. I wanted to tell it easier than it is usually told to get that. To be honest, we need to do this separately in each coordinate neighborhood of B, and then to do it with some steps. I don't want to be precise here, I'm sorry. Let us leave it. Thank you very much for this question, but let us leave it as I leave the details to yourself. Yes, that's true that actually it is not very good to do like that. Yes, I remembered about this problem in one place, but I forget here. Давайте я по-русски скажу. Значит, да, здесь есть большая проблема с тем, что это вообще нельзя говорить про это вот локально говорить. Можно спокойно на самом деле склеить. Я помнил про проблему, что надо аккуратно перевести около кролев, я сейчас скажу. Вот, к сожалению, что-то не казалось, что так можно рассказать совсем просто. Yes, so this is locally, we have this problem, and let me give an exercise to see this problem. Well, so n is at least 1, and so this number is at least 5. And here it is completely important that our process is at least 5. And since it is at least 5, what we see? We see that these images are by Sarn's theorem. These images have measure 0 here. So almost all points are, almost all directions are good. Almost all directions are good. And this means that I can find a direction arbitrarily close to vertical one, which is good. Yes, that's not very easy. Well, actually, that's a crucial point that we want to give. I'm sorry, действительно не продумал лекции, говоря сейчас сходу не могу сказать, как это. Здесь никаких принципиальных проблем не возникает, но как именно это исправляется, я упустил этот момент. Раз совсем предполагаю. Ладно, let us go further. So, what we can achieve? Yes, there is one more problem. There is one more problem. One more problem is that I don't want to change. So first of all, what we do? We choose this direction and we project. And we obtain embedded through v times r n minus 1. And so we proceed in the following way until we go to the very end and finally we get an embedded to v itself. So, one more problem is that actually I don't want to change my phi near the boundary of this. But this projection changes it. It doesn't change. It doesn't. Yes, there is no this problem. The projection doesn't change. Here, yes, so I have prepared to the problem which doesn't exist but didn't prepare which exists. I'm sorry. Yes, so if you believe me that we can do this exercise, then we arrive at the following. We have extended phi to an embedded on this. Next step, which is also not as easy, is that we would like to extend it to an embedded of this place. What actually do we want? In fact, it is
I don't know why you told last proposal to satisfy condition that R plus S bigger than 5.
yes. Well, we can choose good direction because dimension of this manifold is at least 5. Bad directions. There are two reasons why a direction is bad. It can be a line through 2 points or a tangent line. A line through 2 points is a map of 2-dimensional disk times 2-dimensional disk without this one is 4-dimensional. If we know that this is at least 5-dimensional, then we know that the image has measure 0 by Sarsen. If this one was has dimension less than 5, then it could happen that all points are in the image and we have no possibility to project. And it really happens. So it is very important that dimension here is at least 5. In this particular point, this is the only point when it is important. Well, so we have already defined our embedding of disk to V, and we know that this embedding takes C to L1, C prime to L2, and it is very standard in neighborhood of points of these two intersection points. What next we would do? Next, we would like to extend it to, yes, which condition we still didn't use. We still didn't use one of the conditions of the theorem, which is very important. Without it, the theorem is not true. We never use that these 2 points are of opposite sides. It is very important. We never can, just by homological reasons, we can cancel two intersection points which have the same sign. But until now, we never used it. And this is important when we try to make this when we try to extend phi to the whole to add this. What do we want? Actually, I would like to find tangent vectors to vector fields with the following properties. To define this one, I would like I claim that what I need the following. I want to have I would like to introduce orthogonal vector fields on this disk, on file disk. So I would like to have orthogonal vector fields as many vector fields. This will be exactly basis of those two parts. With the following properties. So first of all, these are vector fields, normal vector fields. Vector fields to the disk phi of dt. So I have already embedded this here, and I want to find normal vector fields to it. Well, which properties do I want? First, I want that near P and Q they are standard. Again, here we have near P and Q we have standard situation R and S. So of course, let's formulate an opposite direction. First, along C lies C goes to L1. L1 lies in R. Along L1, I would like that C1, CR minus 1 are tangent to R. And along L2, we would like these vector fields to be tangent to S. So we have this. Let us erase all. Let us erase all. And unfortunately, it is very hard to draw pictures here because an interesting picture appears only in dimension 4. You cannot draw in dimension 4. But let this be S, this be R. Well, we have already this N1, this one is N1, this one is N2, and I want that these vector fields in points of R they should be tangent to R. Why it is important for me? Because I want that this C cross this goes to R in the neighborhood. And similarly with this tangent to S. And in the very small neighborhood of points P and Q, both these are tangent to R, these are tangent to S, and actually I would like them to be constant to this tangent. Because standard are, yeah, sorry, and one more. I would like them to be orthonormal, just orthonormal, and near P and Q, they are standard. Well, now our goal is to construct such vector fields. How to do this? Well, first, recall that now we have small difference. R is oriented and S is coordinated. Well, so let us start with those vector fields which are tangent to R. This one. We would like them to be tangent to R from E to Q. Well, so what I want to say, I choose them arbitrarily, just vector fields tangent to R, and there is no problem to. So first choose C1, C R minus 1 near P. And then I extend them along A1. There is no problem to extend vector fields along R. Or just tangent bundle to R along this R. Any tangent bundle over a segment is trivial. So there are no problems to extend C1, CR minus 1 along A1. And we arrive in a neighborhood of L2. Here we also can achieve the diagonal. But look, what do we see? R is oriented. So we choose them so that they give, say, positive orientation of R. Well, then in P and in Q, these two systems of vector field give both in P and in Q, they are frames in normal bundle to S of tangent space to R is the same as normal bundle to S.
Also need to understand that to A1.
Yeah, of course. I mean that, of course, to get orientation, I need always add from the very beginning tangent tangent vector to tangent vector to one. Let us introduce a notation. Let say U be tangent vector to A1 everywhere along and above, yes, and that V be tangent bundle to the tangent vector to A2. Well, so I would like to say that U C1 CR minus 1 gives, say, positive orientation of R. I can choose them so that they give positive orientation of R. But now the same set of vectors, we can consider them as normal vector at those 2 points. They are normal vector to S. And since we know that these P and Q are of opposite signs, we know that at one of the points, this gives positive orientation of S, co-orientation of S. And then at another point, the co-orientation of S is negative. So we need this. We can choose that, say, P is those where which of sign P plus and Q of sign minus. Doesn't matter which is which. And so we may assume that this provides positive co-orientation of S at P and negative co-orientation of S at Q. Well, what's the next? And now, well, now what we know, we do not know whether V is oriented. So we do not know about tangent bundle of V, if it is oriented or not. But we definitely know that, let us consider tangent bundle of V restricted to the disk. Over disk, all bundles are oriented. So we definitely know that this one is oriented. And also, here this tangent bundle to this disk, and the complement tangent bundle plus normal bundle. Normal bundle is where we try, in this normal bundle, we try to find these sections. And this one is oriented, the total bundle is oriented, so this one is also oriented. Again, since any well, and then what can be? Well, what is important? Sorry. So we have constructed this C vector fields over here, and what I would like to say. Yes, I would like to say the following. Look, of course, again, we do not know whether S is oriented, but it is definitely oriented along A. Along A, we can extend the orientation along A. A is okay. Well, so what is important? I claim that I can find these vector fields at least along S. Why? And along N2. Along this N2. Why this is true? The matter is that look, along this S, along this L2, S is oriented along, and so we can skip, we can change from orientation to orientation, vice versa. Well, so once these two, once sorry. no, sorry. Oh, let us make a break. Sorry, it's time to make a break. I will proceed after it. это ориентация нормального настроения. Вот, то есть смотрите. Вот у вас это 2, да? Так, да? Она, несомненно, не ориентирована. Плохой пример сейчас. Ну, давайте пример я не буду приводить. Совсем маловерных примеров. Но буду говорить, вот есть многообразие. Давайте не ПП, да? И подмногообразие. То у нас есть касательное расслоение к N, ограниченное на P. Это есть касательное расслоение к P, плюс нормальное расслоение к P. Понятно? Ну вот если все ориентировано, если M и P ориентировано, то у нас ориентировано вот это, ориентировано вот это, ну и значит ориентировано. Но вообще говоря, ну вот смотрите, когда у вас есть какие-то расслоения, то у вас всегда, ну, до любой петли изменение ориентации здесь есть, изменение ориентации здесь умножить на изменение ориентации здесь. Да? Вообще, ориентация тут, это есть произведение ориентации здесь, на ориентацию здесь. Если вдоль петли меняется ориентация здесь, меняется здесь, то она меняется целиком, да? Если то она не меняется. Да? Вот, ну, в общем, вот. Так вот, бывает так, что вот это ориентировано, а вот эти не ориентированы. Вполне тоже бывает. Ну, то есть ничего не противоречит, ну и, в общем, не очень сложно построить пример. Когда у вас вот это расстояние ориентировано, а эти два не ориентированы. То есть они одинаково меняют ориентацию.
А просто если даже не сказать, что какой-нибудь известный пример есть.
Какой-нибудь известный пример. Сейчас. Да? Сейчас, одну секундочку. Значит, нам нужно неориентированное многообразие, вложенное во что-нибудь неориентированное. Ну вот можно взять тут 3, да? Это что такое? Это такое скрученное произведение S1 на S1. Да? Вы берете цилиндр, и склеиваете по обращающему ориентацию. Да? А давайте рассмотрим такое же трехмерное скрученное произведение S1 на S2. У вас есть теперь цилиндр S2 на S, да? И вы его тоже по обращающему ориентацию скрепите. И это не ориентированное многообразие, и это не ориентированное. Это обычное скрепение. Это трехмерное. Но теперь вот это сюда элементарным образом вкладывается. Ну, просто каждый S1 вкладывается соответственно. Ну, а обращающую ориентацию изоморфизма можно согласовывать просто симметрии. Вот. Ну вот эта штука, это не ориентировано, она коориентирована.
Ну, то, что коориентировано, это видимо.
Коориентировано, потому что S1, S2 и коориентированы, у нее есть внешняя название. И вот она там пишет спереди. То есть у вас как бы вот S1, как S1, S2. Вот у вас S2, да, а в ней S1. В качестве обращающего ориентацию автоматизма вы, например, берете относительно вот такой вот диаметральный плоскости. S2, а вот на ней маленькая такая S1. А вот это вы берете в качестве обращающего ориентацию автоматизма, вот которого вы склеиваете. Ясно. Смотрите. Чтобы склеить, вам надо выбрать обращающую ориентацию гомеоморфизм между его краями. В качестве обращающего ориентацию гомеоморфизм возьмем симметрировать, но такой выпуск. Вот, можно было и экватор нарисовать, я все-таки экватор. А S1 возьмем вот здесь вот так симметрично. Вот так должен, да? Тогда у нас вот, честно получается положение вот такое. Но вот здесь есть вот оно. Нормальное внешнее векторное поле. И оно отлично уважается этим гомеоморфизмом. Поэтому вот эта штука здесь будет иметь четкое нормальное векторное поле, значит оно будет иметь тривиальное, ну да, даже не только ориентированное, а в данном случае тривиальное нормальное. Но естественно, оба из них не ориентированы. Так, давайте продолжим. Я прошу прощения, я сейчас закопался на абсолютно пустом месте, мы сейчас раскопаемся за секунду. Вот. Well, let us fix what we have discussed. We took standard vector fields Xi, which are supposed to be tangent to R along L1. Well, we extend them in tangent to L1 way along L1, yes? And we arrive again at standard vector fields here. Well, so that this unit vector, standard vector U is tangent to L1, and so this one is positive orientation of R, and hence at one point it is negative orientation of S, and at another point it is positive orientation of S because of this property. Now I want to extend C1, CR minus 1 along S. I was wrong. I don't want to consider this at the moment. I still want to consider C1, CR minus 1. So now I say that look, what I want. I want to extend. Let us consider S L2 in model cases. So now I draw another picture where we have this L2 in S. This is L2. And we have C1 CR minus 1. But also, sorry, I don't want to draw. I prefer to draw the whole L2 and the whole S in the same way. I'm sorry. In my picture, I cannot. I prefer to draw R two-dimensional, so I have to draw S one-dimensional. But it is not supposed to be one-dimensional. Here I got this one, and look, here I have at the points, here I have U, and I have this C1 CR minus 1. They form orthonormal frame to S together with U. So here U C1 CR minus 1 is orthonormal frame in normal bundle to S. Well, the endpoint, at this endpoint, and at this endpoint also, I have that it is orthonormal frame, but with opposite orientation. Well, but I would like to consider here, look, here U goes, looks in another direction, say, well, in our disk. Well, so I would like, if I consider at point P, I consider U C1 CR minus 1. Then at point Q, I would like to consider minus U C1 CR minus 1. This is again after normal frame in normal bundle to S. Well, but well, now actually what I want my to extend this C1 CR minus 1 along L2, but I would like them both. I would like that C1 CR minus 1. What are requirements for C1 CR minus 1 along L2? First, I want them. I further want to consider those frames which are tangent to S. The moment I have it, but I want them to have further. So I would like that this C1, C1, they should be orthogonal to S. So I want that they are orthogonal to S, but I also want that they are orthogonal to disk. I also want that they are orthogonal to phi of T2. Well,
is it supposed to be point Q?
yes.
And can you tell again why is it minus?
I just want to take it minus. Why? Because I say that, okay, if I take minus here, then these two frames have same orientation. No. The matter is that if I have with plus, then they have opposite orientation. They provide opposite co-orientation on this. But now these two provide the same co-orientation on this. The same co-orientation of this. What I want to say, I want to say that look, we have got, and now I will explain why it's minus. Along this loop L2, we have normal bundle to S. Well, not normal bundle to S, we can restrict it to L2. So this is a bundle over, vector bundle over 2. But I'm interested not in it, but I'm interested in its intersection with normal bundle to, I would like to consider normal bundle to S, have normal bundle to disk. I would like my C1, CR minus 1 to be orthogonal both to S and to the disk. Well, so this is a subbundle of codimension 1. Well, because in the disk there is exactly one vector which is orthogonal to S. Yeah. This is a standard picture in standard disk. And how does this vector behave? Here is this vector. We start from U, And if we extend it continuously, then we arrive to minus. And this is exactly why I want to have minus here. This bundle is oriented. We have co-orientation of S, and we have chosen orientation of well. So this is actually this bundle is this one plus one-dimensional bundle spanned by this vector. So to obtain orientation here, I need to choose orientation in the complement bundle. And this orientation, if we start from U, we arrive at minus U here, not at U. Just at this, the picture is as follows. And hence, so if what can we say that if these two provide the same orientation, the same coorientation of S, then it implies that C1, C R minus 1 provide the same orientation of this bundle. So once more, this bundle is, all bundles of the two are oriented, but the connection, we would like to obtain orientation of this bundle from the orientation of that bundle. To see the correspondence between orientation here and orientation here, we need to choose additional vector, which is additional, which if we adhere to, then we get this one. We should orient one-dimensional bundle which is normal to S but tangent to this. And this one-dimensional bundle, if it starts with U, then it finishes with minus U. And this is exactly what it is. So we know that if those two guys provide the same orientation of S, and we know that this is true, then this one provides the same orientation of this bundle in both frames. And this is exactly the condition when two frames at the endpoints of a segment provide the same orientation of some bundle, then they can be extended. So if we have two frames with the same orientation, then we can continuously form one of them to another. If they have opposite orientations, then we can. But exactly the requirement that these two points have opposite sign, it exactly guarantees through this argument that we can extend C1, CR minus 1 to the well, what do we see at the moment? At the moment, we see the following: that we have extended C1, CR minus 1, but not over the disk, but only over its boundary, only over to we have extended it along this path and along this path. And that's the case, so we have well-defined C1 and CR minus 1 along those two paths. Well, what about ends? Let us first discuss ends and then try to go inside this. With ends now it is everything is trivial. Why? The matter is that so at the moment we have these X's. So up to now, we have defined C1, CR minus 1 element L1 and L2, so that C1, CR minus 1 are orthogonal to the disk. C1, CR minus 1 are tangent to R along L1, and C1, CR minus 1 are normal to S along L2. These are exactly our situation. And now we would like to extend. Yes, and also they are standard near endpoints. I just was correct. Now we would like to extend ends, but at the moment, again, only along L1 and L2. But what do we want about these ends? Look, the situation is as follows: that we have this two-dimensional disk. Well, we have this two-dimensional disk, and what do we? Well, let us start with extending endless along S. What do we want to have along S? Along S, we know that we would like that these endless are tangent to S. Well, and so I want to say the following. Sorry, it is much easier than I would like to say that the whole vector bundle over the whole heap. I would like to make one. I would like to make one change notation. It is very nasty to write everywhere 5 but that's just denote this value. So if I want to restrict the tangent bundle to our discrete, then what we get? We have the just tangent bundle. Well, now we have and we have normal bundle, but inside this normal bundle T2, we have already well, and what we know? We know that this is oriented. Well, everything about over this, everything is oriented. So inside this two-dimensional disk, we all inside this normal bundle, we have already chosen so sorry, I always sorry, I don't want to say about this. I want to consider only on the loop now, only on one-dimensional circle. So we have tangent bundle of this loop. We have already constructed these C's, and we have some additional bundle. So this is orthogonal complement to this R's in normal bundle to the disk. So in the normal bundle to the disk, we have already constructed C1, CR minus 1, and we want to consider the complementary subbundle. Everything is oriented. This one is oriented, this one is oriented, so this one is also oriented. So this is an oriented vector bundle over S1. Over S1. But all oriented vector bundles over circle are trivial. So it's a trivial, hence I can choose the basis frame width. And what we get, we immediately see that these atoms, they are orthogonal to C1 CR minus 1, hence they are automatically orthogonal to R along L1 and tangent to S along L2. Since this one, the C is orthogonal. So we immediately get echelon at S minus 1. They are tangent, are normal to R along A1, and they are tangent to S along A2. Well, and actually until this point everything is easy. I'm sorry for describe it in a slightly difficult way, but it is not hard to now. But now we have to do one thing which is less difficult. The matter is that we would like to extend our vector fields to the interior of the disk. And what do we see? We only want on the interior of the disk. We do not have any further restrictions of these Caesar atoms. We want them to be tangent to submanifold or normal submanifold only on the boundary. Inside, we just can have any, but we want them to be frames, orthogonal frames. But any frames just orthogonal to the disk. Well, so what is interesting to us is the following: that we have normal bundle over disk. This is bundle of dimension Rs plus R minus 1 over disk. And what we see, we have already chosen trivialization of this bundle. Frame means trivialization. We have already chosen basis of sections of this bundle. We have already chosen them over the boundary of the disk. Below the boundary we have chosen. And I would like to extend these vector fields to the whole boundary. But this is not always possible. This is just we have an abstraction. And let us describe this abstraction. Look, what do we see? Of course, this bundle over D2 is trivial. All bundles over D2 are trivial. Well, so we can reformulate our this one is isomorphic to D2 cross R S plus R minus 1. So we can reformulate this in the following way. That look, we just have a basis of R S plus R minus 1 dependent on a point of circle. We would like to extend this map to the disk. R minus 1 plus S minus 1 is R plus S minus 2. Sorry. So what actually we have? We have a map from S1 to all frames of orthonormal frames of R plus S minus 1. What is orthonormal frames of R minus S plus S minus 2? The set of orthonormal frames is nothing but yes, and all they are positive oriented. But they are nothing but the group that is special orthogonal group. Set of frames is exactly the orthogonal group. Yes. So we have such a map. have basis along the boundary, we have this map. And we would like to extend it to the map of the disk here. If we succeed to extend it, then we have frames over the whole disk. Well, but of course, this is not always possible. This is just the question about the fundamental group of this group. And what is the fundamental group of this? Is this normal or not? Well, what is the answer? The answer is that if you take n equals
When it's
n equals to 1 is not interesting, this is just a point. So this is Z, this is circle. Yes? If you have S3, this is Z over Z, since this is a standard fact that this one is arbitrary. Well, if we have fibration,
we can use fibration.
yeah, we can use this standard fibration that SON goes to, we can consider first vector of the basis. The fiber is SON minus 1. And writing, this is a good exercise to write down exact how the sequence for this vibration, and to obtain that the same answer is true for all n greater than or equal to 3. Well, so it may happen. In our situation, of course, r plus s minus 2 is at least 3. Yes? So in our situation, we are in this situation. We are never in that situation, but we are always here. But it may happen that our task isn't consistent. That we get into non-trivial element here, and we cannot succeed to extend our fields to the internet. Well, what to do? But, well, the answer is very easy. That, okay, we have freedom to change these vector fields. We look, the matter is that we not only know that this is Z over Z, but we also know that from all the stuff, we know that V1 of SOM, we have such a map whenever M is less than N. And it is surjective provided that M is at least 2. This is either Z or 2, it is surjective. And now, at least one of those two maps, and at least one of those two either R minus 1, or actually, we even know precisely, S minus 1 is always at least 2. Yes? So, we can change ethos. We can change ethos, say, locally near some point here, so that they remain tangent to S. We just change them locally to correct our homological. We can always change them here by opposing any prescribed homological. So that they are still tangent to S, orthogonal to this, then we can guarantee that this one is completely trivial. And then we can take this extension.
Сейчас мы локально меняем.
Да, мы локально в окрестности некоторые точки на S. В окрестности in a neighborhood of a point on S. What we have? We have this ethos near quadrant. Why this is important? This is important since we can organize any prescribed element of the fundamental group, but actually it is only one, by changing only ethos, not changing x's. But what do we see in the neighborhood here? In the neighborhood here, we have, in this small neighborhood, we have this tangent bundle to S cap normal bundle to this. This is exactly the bundle in which ethos are bases. So we have basis ethos here, and we can choose trivialization here so that locally it is just standard basis. But we can, along this small path, we can replace this ethos by some bases which organize an non-trivial element in the scope. And then after such replacement, the total homotopy class of C's and F's together will change, and we can achieve that it is trivial. Well, so what we get? We get that finally all our C's and ethos are defined over the whole disk. Well, so finally we achieve that. Look, we have defined these vector fields over the whole disk so that they are orthonormal frame. They form orthonormal frame orthogonal to disk in all points, and also in points of on L1 we see that C1 CR minus 1 are tangent to R, and ethos are normal to S. And on L2, we have that C's are normal. Normal to R. There is no S. Along L1, we see only R. There is no S at points of L1. And here we have these are normal to S, and ethos are tangent to S. Okay. And now we use exponential map to extend our phi. So up to now phi is embedded in a disk, but now we can extend it to embedded on disk cross R cross S by using exponential map. And we actually there is one point where we need to have some accuracy. I want to use exponential map to provide phi from disk cross R minus 1 cross R S minus 1 to our T. What does it mean to consider exponential map? This means that if I would like to compute f of x, y, z, well, then I need to take phi is already defined on P2. So I need to start. I have already this P2. I would like to start from a point phi of x here, and I would like to consider geodesic which goes in direction y1 c1 plus y r minus 1 c r minus 1 plus z1 delta 1 plus z s minus 1 and s minus 1. This y and z just go as direction. I should start considering this geodesic, and but of course I will slightly on small segments. Our geodesic map is injected, but actually, what is the technical point here? The technical point here is that generally this geodesic is of course tangent to R. Well, say what I want. I want that I want to guarantee that phi of C, this is C, and this is C prime. Phi of C cross R minus 1 is in R, and phi of C prime cross S minus 1 is in S. It is not completely true. The matter is that if we have zeros here, if we start from C, so sorry, if we start from C and we have zeros here, then our geodesic is tangent to R, but not in R itself. And similarly here, it is tangent to S, but not S in S exactly. There are two ways to solve the problem. These are just technical points, so I just give you some ideas and then we go into it. One possibility which is realized, say, in Newton's book, Differential World Theory, is that before doing all this, we choose a good enough metric on we can choose metric so that our submanifolds are totally geodesic. So that any geodesic which is tangent to a submanifold necessarily stays into this submanifold. It is a good technical lemma that just if we have a manifold and two transversal submanifolds, then we can always choose such remaining metric so that these submanifolds are totally geodesic. It is not. And if we do this, then we have no problem with it. Then if geodesic is tangent to R, then it stays in R, and we indeed get our. Another way is not to choose a special metric, but to slightly change our exponential map. So we can we can behave like that in points which are far from R, far from this N1 somewhere here. We can do just usual geodesic, usual exponential map. But in points on N1, we can consider only exponential map projected onto R. And then we can use conditional unity, we can change from one to another. This is just some idea. Maybe easier way is, as Newton did, to choose metrics so that so the geodesic, then there's no. Well, so I'm sorry. It took quite a long time, but after all this, we get through all difficulties and we have proved we can do it. And it is really very, very useful. And now let us just see how to use it. And we let us consider use this Whitney trick to prove the following theorem on cancellation of critical points for a Morse function. I would like to remind you that, well, we return to our situation. We have such a triple. V0, V1, W. This W has dimension n. And we have here a Morse function. We have here a Morse function. And assume that this Morse function inside, as usual, V0 function is constant on V0, constant on V1, and no critical points on the boundary, and only two critical points inside. So we have two critical points P and Q of indices lambda and lambda plus 1. And I would like to cancel these 2 points. And I recall that we have already proved that, as usually, we have this function phi, we have gradient like vector field C. And we have already proved that if there is exactly one trajectory from Q and P, well, then we can cancel. We have already proved this. But it turns out that under some very violent conditions, it is not important that there is only one trajectory, but it is only important that the algebraic number of trajectories is plus or minus 1. So I recall that for each trajectory we have a sign. And well, and we have introduced that incidence coefficients, which are algebraic numbers of trajectories for Q phi. Of course, always we assume that this C is chosen so that right-hand sphere of P is transversal to the right-hand sphere of Q, so that always in transversal position, and we can define this sign. And now, so theorem is as follows. Let us formulate it. Precisely. Theorem which we need is as follows. Suppose that n is at least 6, and this is exactly what we need for H cobordism. For H cobordism, we consider H cobordism of 5-dimensional manifolds, and the cobordism itself has dimension at least 6. And W, V0, and V1 are all simply connected. So all the three are simply connected. Well, and assume that this Q pi, QP, which I recall that it is the same as the algebraic intersection index, we can consider here some level B, and in this level we have a right-hand sphere of P, and we have left-hand sphere of Q. And this is the same as their algebraic intersection index. And we require that it is plus minus 1. So algebraic number of trajectories from Q to pi to P is equal to plus or minus 1. Then we can cancel those 2 points. Then W is diffeomorphic to the 0 first. This is a very strong theory. Earlier, we knew this theorem for the case when there is exactly one trajectory. But this is a condition which is completely impossible to check. It's very hard to organize that there is exactly one. But this is a homological condition. This is much easier for you. So this is very important improvement. And I would like to add one condition. This theorem is true in this generality, but I will prove it under. I don't want to. I want to prove it with some additional condition. I want to add here that lambda is not 1 and not n minus 1. It is not important for the statement, but it is important for the proof. 1 and n minus 1 are special cases that we need to think of them in a special way. And I don't. We will not need this theorem in this situation. So I add this, but this is not important for the statement. The statement is true for 1 and minus 1, 2. Well, actually, different. Actually, the idea is that under that conditions, we can make an isotope here, so that to organize these 2 spheres, we can change our gradient light vector field. I recall that change in gradient light vector field, we can organize any isotope of this vector sphere, and Whitney trick will allow us to make an isotope which so that the after this isotope there is exactly 1. Well, let us do it in detail. First of all, I claim that I would like to use this VT inside this V. And the first thing which I need is it is very usually VT trick is used when V is simply connected. Otherwise, it is very hard to understand why something is contractible. So first of all, I would like to understand that this V is connected. A priori, we know that only these base levels and the whole topology is connected. Why it follows that V is connected? Look, let us consider the figure which is drawn here. Let us consider V together with attached left-hand disk of Q and right-hand disk. So let us take this union of the levels at V. V cup left-hand disk of Q cup right-hand disk of P. So this is V with 2 disks attached. Well, before doing this, let us also make one simplification. Look, this index lambda. Well, it can be. It is not 1 and not n minus 1. Let us also for a moment assume that it is not 0 and not n. These are special cases which are very easy. Well, so let us assume that lambda is in between 2 and n minus 2. And actually, I can also assume that lambda is not n minus 2. Why? This is not an assumption. If lambda is n minus 2, then we can always reverse this function. We can always change direction of this function. Just and then lambda will be replaced by n minus lambda. So if lambda is n minus 2, and since n is at least 6, we can easily pass through n minus 2 and minus 3 to points of index 2 and 3. So this is not a restriction at all.
Наверное, иметь в виду, что нужно здесь n-3, потому что лямбда не может быть равно n.
Well, yes, here is n-1. Sorry. Here it's not n-2. Sorry. And here it's not n-3. Yes. So sorry. Here I require that it's not 1 and not n-2. 0 and n-1 are special cases which we will consider later. And n-3 is case which is easily obtained from by reversing the picture. So we can always assume that lambda is between 2 and n minus 4. We can always consider that lambda is in this. Now let us compute the dimensions of these. Which dimension has left-hand disk of Q? Q has index lambda plus 1, so this left-hand disk has dimension lambda plus 1. Well, dimension of left-hand disk is equal to index over point. Dimension of right-hand disk is equal to n minus index. So we have n minus lambda here. What do we see? We see that both are these 3. Okay? So, what can we say? We know very well that if we attach to a space some to any cells of dimension of these 3, then we do not change fundamental group. Fundamental group doesn't change when we attach cells of dimension 3 or 5. So we know that fundamental group of this guy is the same as fundamental group of D. And now, what can we say about this set? The claim is that this set is a deformation retracted double.
Around n minus at least 4. I mean, can we change orders of number from 2 to n minus 3?
We will need this later. At the moment, it is not n minus 3, but I want to have n minus 4 here to be able to apply it. So it is a deformation tract of double. This is more or less what we have proved. If we look in the upper half, we start gradient flow from C in decreased dimension. And we arrive either at this level or at this. We have done it in detail when we discussed what happens when we and in this part we what happens when we pass through a critical point. And in this part we consider gradient flow in increasing dimension. And they arrive exactly to this set. Well, so W is simply connected. So we see that this one is trivial, and hence this one is trivial also. Well, so we see that V is simply connected. Now, I would like to use.
Нельзя было сказать, что просто получается на определение ручки.
Можно. Да. Now let us consider напряжение ручки, ну, на хирургию отличается. Напряжение ручки отличается то, что ниже. Вместе содержит сам слой. Напряжение ручки отличается, как мы всегда смотрели, многообразием плоского различия. А сейчас не интересует сам слой. Но тоже так можно. Ну, может быть так. Well, so anyway, V is simply connected. And I would like to apply Witten trick for this submanifold, for which submanifold. I know that left-hand disks are always oriented and right-hand disks are naturally coordinated. This is exactly how we find this equation. And so I would like to take, for oriented one, I would like to take, but I would like to consider not disks but spheres. I would like to consider submanifolds in V. So for R, I take the left-hand sphere of U. Well, and for S, I take a right-hand sphere of E. This one has dimension lambda. This one has dimension n minus lambda minus 1. Together, the sum is the dimension of V. Yes? And what else do we have? Yes, what do we know about lambda? Yes, R plus S equals n minus 1, and is at least 5. The main condition is satisfied. S is at least here, we need this n minus 4. S is at least 3. Well, what else do we need? What else do we need to apply this theorem? We need that this one is integer. But what is V without S? What is V without S? S is that V, well, V without S, without this here, its deformation tract is, if you take V without S, sorry. Then this is the same. V without S is the same as V0 without left-hand sphere of V. On the complement of this figure, our flow is just diffeomorphism. So we see that V without S is diffeomorphic to V0 without left-hand sphere of P. Left-hand sphere of P. Left-hand sphere of P, its dimension is this one has dimension lambda minus 1. this dimension is very small. It has large dimension. The dimension is 4. So throwing away this subset doesn't change the fundamental group. So since V0, we know that V0 is simply connected, it follows that this one is also simply connected. So we just see that both are simply trivial, so it was well, so we are explicitly under the condition of this theory. What it says? It says that we can make an isotopy, we can achieve that we make an isotopy, say, of this green sphere, we can cancel and cancel and cancel pairs of points with opposite signs. And if the algebraic number of points is plus or minus 1, yes, this conditional existence of A is trivial, since both our R and S are connected and the dimension is 2, so it is also fulfilled. And we can use this without any problems, and we cancel and cancel and cancel points until we get only one of them. All pairs, each pair of opposite signs can be cancelled. And once we know that algebraic number is plus minus 1, then we reduce this to the case of exactly 1 point, and then we apply theorem which we have already proved. Exactly 1, project, and then we are done. Well,
Вопрос.
Да.
А вот когда мы говорим, что вы объединились двумя дисками, это информационная редакция, вот у нас не будет проблемы с тем, что у нас траектория приходит с точки критической до бесконечного времени.
Помните, там мы вот когда как раз обсуждали, а когда будет, там в конце надо проектировать, когда мы на ответственность пошли уже, то нам надо проектировать тупо по прямой. Да, там совершенно верно, просто мы уже все тогда. Действительно, если делать напрямую, то будет проблема. Yes, we have 5 more minutes. Let us discuss what happens in cases 0 and then minus 1. Yes? They are, again, this is the same case. 0 and then minus 1. These are two cases which are obtained from each other by reversing the picture. So we can consider only the case of 0. But actually this case is hopeless. Look what happens in this case. The matter is this case is as follows. We have a local minimum here. P is critical point of index 0, so it is a local minimum, and Q is index 1. Well, there is an important observation. Of course, if we have a manifold of positive dimension, then it has, even if it's orientable, it has two orientations which are equally matched. Where they are, nothing of them is preferred. But for a manifold of for a manifold of 0 dimension, there is one preferred orientation. We have positive for a point, we have positive orientation and negative. What I want to say here. Here the situation is where it's completely, we do not give any unique trick. Everything is completely is very standard. The matter is that, look, here right hand disk of P is of full dimension. Yes? Yes. So it's of full dimension. And left-hand disk of Q is just an arc. Well, and if we consider intersections of this intersection, then it always has positive sign. Zero-dimensional submanifold has only one orientation, one prescribed orientation positive, and full-dimensional submanifold has a prescribed positive orientation, and of course they always agree. So this sign is always plus. So if it is algebraically plus minus, it is always plus one. We always have exactly one trajectory. Actually, if we have just only two trajectories from Q, if both of them come to P, then we have here plus or minus 2. Actually, no, we have actually 0 since these two are open trajectories. So in this situation, we automatically have exactly one trajectory. So this case is actually trivial. In cases 1 and n minus 2, they are, you may consider them as exercises. This is actually a good exercise, but here we have some problems. Again, they can be turned to each other. So 1 is enough to consider 1, but we have some problems with simple connectors. The matter is that this disk is two-dimensional, and so from this one is simply connected, but it doesn't follow that it can be simply connected. And also we have some problems that are one-dimensional now, and so we have a problem to come from one, if we would like to cancel some intersection points, it may be difficult to pass from one to another in R without meeting other intersection points. So there are some problems, but still it can be done. It is true. Well, that's also. Unfortunately, well, I will not be able to prove H-cobalt theorem in all details. The next lecture will be the last one, and I will try to give some ideas to describe the general logic of groups. But this is a very important crucial step. We can cancel pairs of points under some homology conditions. Well, экзамен я не успел. Давайте еще давайте следующий вопрос. Я разошлю.
При этой условии не выполнено, то что сейчас хотя бы 5, а сейчас 3. Она есть какой-то примерно результат.
Там на самом деле сейчас ну, без больше геометрии это на самом деле довольно мелочь, потому что более-менее резко. Ну, это такая, это не очень важно. Вот, а вот то, что этот процесс больше идти, сейчас, вот, я тебе вспомню, что там в 4-первом. То есть в 4-первом случае просто вообще ничего не делать. Да? Нет, процесс научный ничего не делать. В 4-первом, по-моему, тоже неверно. Там есть тонкость, тоже, я забыл. Вот. То есть там ответ такой, ну, проблема в чем? Проблема в том, что куда-то у меня проблема в том, что мы когда накатить наши любые и сделать только какого-то примерного диска. Этот примерный диск надо сделать, чтобы он был не сам пересекающий. Нет, сейчас в этой самой размерности 3 очень легко понять, что это не я, да? Потому что, вот, хороший вопрос, хороший пример. Размерности 3 все просто. Знаете, вот такая вот штука есть. Спинной. Давно доверяет. Если мы возьмем вот такой вот диск и вот такой вот другой вот этот будет вес, вот, то точки разные. Ну, то, что многообразие не замкнуто, это полбеды у нас далеко. Границы все можно избежать. Вот. Вот. Все. Если бы можно было сократить, то у нас бы дисплей не было. Например, это и принципиально. То есть, на самом деле, вся теория, если бы вдруг Уит не работал в размерности 3, вся теория примерно топологии настолько тривиальна, что просто ничего не оставалось. Вот.
То есть там, грубо говоря, можно было бы узлы расцеплять?
Ну, там можно было расцеплять все, у чего нет правительства препятствий. Если сплейхов нельзя расцеплять. Ну, нельзя было бы. Как нельзя? Вот, нельзя было бы расцеплить, потому что его алгебраическое коэффициент 0. Тут трюк не поможет. Трюк позволяет уничтожать самопересечения, как сказать, когда у них противоположные значения. Вот такое вот. Да, вот такое, там, всякие кольца параллел, реально. Вот, то есть это, ну, трюки не принципиальны, теперь, по-моему, размер 4. Тоже я вот размер 4, значит, вот, я прошу прощения. Ну, то есть, заверно нет такой теоремы, а вот если там прямо пример, когда это неверно, или там до конца так непонятно. А в трех просто, знаешь, ты вот, ладно. Можно позвонить. Ну, я все. Да. Значит, да, да. Ну, может считать, что они есть, да.
Ну, я уже где-то на первой лекции. Ну, то есть, если, наверное, прямо сейчас все это слушать, наверное, понятно.
Честно говоря. Честно говоря.
Ну, конечно, я решил старался вникать. Я когда долго что-то рассказывал,